Welcome to Spaceverse, your portal to cosmic adventures. Imagine a butterfly-shaped nebula fluttering in deep space, not with wings, but with glowing lobes of gas and dust, twisted, sculpted, and illuminated by the chaos of creation itself. This is LINS 483, also known as LBN 483, a remarkable example of what happens when two young stars are born in close quarters, surrounded by the material from which they're made. LBN 483 sits quietly in the vastness of space, about 650 light-years away. It may seem serene in images taken by the James Webb Space Telescope, but what we're really looking at is stellar mayhem, a bipolar outflow of gas and dust, exploding outwards from the tumultuous birth of not one, but two stars. This breathtaking hourglass shape isn't just beautiful, it's the signature of star formation at its most energetic. And JWST has imaged this cosmic drama in stunning infrared detail, revealing features we could only guess at before. Let's begin at the heart of the story. Every star begins in a gravitationally collapsed cloud of molecular gas. As material collapses under its own gravity, it starts to spin, forming a dense core that will one day ignite and become a star. But here's the twist: this isn't a one-way process. Even as stars form by accreting material, they also eject some of it back into space through jets and outflows. In LBN 483, these jets and radiation winds blast outward in bursts, slamming into the surrounding cloud. Each eruption pushes the nearby gas and dust outward, sculpting intricate shapes in the nebula. These powerful interactions between inflowing and outflowing material are what gave this nebula its now iconic butterfly shape. The process isn't smooth or uniform. The jets are episodic, occurring in bursts, usually triggered when a young star takes in too much material too quickly, almost like a stellar burp. These outflows are narrow and fast, while the slower ones can fan out more widely. Now, what makes LBN 483 especially exciting is that at its center lies not just a single star, but a binary system, two protostars caught in a dance of gravity. This wasn't known until 2022, when a team led by Aaron Cox of Northwestern University discovered the second lower-mass companion using ALMA, the Atacama Large Millimeter or Submillimeter Array in Chile. This discovery was a game-changer. The presence of two protostars drastically changes how outflows interact with the surrounding material. Think of it as two competing garden hoses blasting into a muddy sandbox. The complexity increases exponentially. Although we can't see the stars directly in the JWST's near-infrared camera image, they're just too small and shrouded in dust, astronomers can infer their presence. If we could zoom into the heart of the nebula, right between its bright lobes or wings, we'd find these two stars nestled within a dense, donut-shaped cloud of gas and dust. This dusty torus is feeding material to the protostars, allowing them to grow. But it also blocks light, especially in the middle of the image, which is why we see dark areas between the V-shaped bright lobes. The bright lobes themselves are illuminated by starlight escaping through the polar holes in the dusty donut. Now here's where things get visually and scientifically interesting. JWST has revealed an incredible level of detail in the lobes. You'll notice twists, arcs, and crumples, which are not just random, they're evidence of where jets and outflows are colliding with both the surrounding nebulous cloud and with earlier outflows. In fact, the bright orange arc captured by JWST is a shock front, where a newer jet is plowing into denser material. There are also light purple structures. Those are pillars of denser gas and dust, standing strong like buttes in the American West. These pillars resist erosion by the outflows, just like ancient stone structures weathering centuries of wind and rain. Let's talk about magnetic fields, because they are crucial players in this cosmic dance. As the jets stream outwards, they follow the paths carved by the nebula's magnetic field. Observations by ALMA detected polarized radio waves coming from extremely cold dust near the center of the nebula, dust so cold that even JWST couldn't detect it. These polarized signals reveal the orientation of the magnetic field, which in turn tells us how it's shaping the nebula. Here's a key finding: at about 93 billion miles, or 1,000 astronomical units from the stars, roughly the distance from our Sun to Voyager 1, the magnetic field takes on a 45-degree counterclockwise twist. This kink is likely caused by the movement of the protostars themselves. Right now, the two protostars are separated by about 34 astronomical units, or 3.2 billion miles, slightly farther apart than the distance from the Sun to Neptune. But simulations suggest they were probably born farther apart, and then migrated closer together. When one star moves in, it alters the system's angular momentum, which can't just vanish, it has to go somewhere. And where does it go? Into the magnetic field, which is then twisted like taffy by the motion of the stars. This twisted magnetic field is carried outward by the outflows, shaping the nebula's wings in a very real, physical way. This is why studying LBN 483 is so important. It's not just a pretty cloud in space, it's a natural laboratory for understanding how stars are born, how they grow, and how they interact with their environment. Most star-forming regions we study, like the Orion Nebula, are massive and crowded, filled with dozens or even hundreds of protostars forming at once. LBN 483, in contrast, seems to be relatively isolated. That means we can study it without the noise and interference of a crowded stellar nursery. It offers us a cleaner view of the dynamics of a single binary system and its direct influence on its surroundings. By carefully observing the shapes and structures formed by the jets and matching them with numerical simulations, scientists can tweak and improve our models of star formation. Every detail we learn from LBN 483 helps us understand how the stars we see at night, and even our own sun, were formed. And just maybe 4.6 billion years ago, as our solar system was forming in a similarly chaotic cloud, some alien astronomer was watching, peering into a dusty cocoon where our sun was just beginning to shine. Now here we are billions of years later, observing another young star system in LBN 483. And perhaps billions of years from now, the inhabitants of that binary system, now quietly forming in the heart of this butterfly nebula, will be watching the sun's final days long after we're gone. Two separate moments in time. Two different civilizations, each witnessing the cosmos from their own place in space and history. Yet they are connected by the same timeless cycle, the birth of stars from clouds of gas and dust, their long evolution, and their eventual death, spreading the seeds for new beginnings. This cosmic rhythm links the young stars in LBN 483 with our own sun's past and future, showing us that across billions of years and light years, everything in the universe is part of one grand, ongoing story. That's the real beauty of LBN 483. It's not just a pretty nebula. It's a reminder that we are part of an ancient and ongoing story written in starlight and scattered across the galaxy. If you enjoyed this dive into the science of star formation and the amazing structure of LBN 483, don't forget to like, subscribe, and hit the bell so you don't miss future journeys into the cosmos. The universe has many stories to tell, and we're just getting started.